what I was having you measure in numbers 1A and 1C, right? What I was having you measure was called the natural frequency. It's the frequency at which a system tends to oscillate. If you watch this skateboarder go back and forth, they're oscillating naturally at a frequency of about zero point 0.5 hertz. Every second, this person does about half of a complete cycle, half of a there and back again cycle. And natural frequency is really important for understanding sound because if you know the natural frequency of something, you can make it resonate. So, resonate has a big definition, it's got lots of parts to it. So, let's break it down and then we do the demos for resonance. And oh boy. Okay, so when I talk about resonance, this is where you have some sort of oscillating system, like this guy pushing his dog in the baby swing. He's got this naturally oscillating system, right? And he's applying what's called a periodic force. He's applying a force at the system's natural frequency. And that causes his dog to increase amplitude as he swings. So let us go take a look at how this looks in real life. Let's say we wanted to push a person on a swing. We would need to apply a force. We want to apply that force every few seconds at the natural frequency of the system. And what we'll see is an increase in amplitude. If you've never pushed a child on a swing, have you guys ever seen kids go on a swing and just like completely mess up, like not know how to make themselves go higher?
Yes.
Right? You ever see kids do on the swing and they do like this, and they're like, "Oh, the faster I go with my legs, the more swinging I get." That doesn't work because they're pumping their legs at the wrong frequency. What frequency do they need to pump their legs at? Well, watch this. The frequency that this system naturally wants to oscillate at. So I'm going to try to keep me still. This rate, this is the rate that I need to pump my legs at. If you were pushing a kid on a swing, you would want to push them at exactly this rate, right? Now, let's say a whole class just walked, hey, a whole class just walked by, they're like, why is there a swing there? Let's say you push it the wrong way, right? Let's say you push at this rate, fast as you can, right? If you imagine trying to push a kid as fast as you can on a swing, going like this, right? Sometimes you'll hit them and it'll make them go higher. But sometimes they'll be going back towards your hand and you're just slapping them on the back now. You have to push them at exactly the same rate that the system wants to oscillate at. And when you do that, let's see if we can get it to go. A little bit. There we go. If you go at exactly the same rate the system wants to oscillate at, you get resonance, which means the amplitude of this motion gets larger and larger. And this has lots of applications besides just swinging. Hey everyone, so here's one we don't want. Let's say I have this system set up with two springs, 1, 2, and this cart, right? Now, with a swing, we want resonance because then we get a higher amplitude and that makes swinging more fun. But what if I had a system that could oscillate that represented something more critical, right? If you don't have a fun time swinging, that's fine. But what if this system represented a bridge? Let's say that these two springs represent the tension of the wires holding a bridge in place, and that this cart represents the bridge itself. If you've ever seen the Tacoma Narrows video, the bridge collapse in the 1940s, what actually happened is instead of a spring moving back and forth, the wind was applying a periodic force at exactly the right frequency to cause this amplitude to increase. So to help demonstrate this, I have what's called a mechanical oscillator, and I'm going to start it with a low frequency. Let's start it with a frequency of about 1 hertz. That means every second, It goes up and down once. This is a frequency of 2 hertz, 3 hertz, 3 up and downs per second, 4 hertz, 5 hertz. And notice that at all these frequencies, this is a stable system. Our bridge is not moving, we're good. But what happens if the wind suddenly pushes at the wrong frequency? The natural frequency for this system is about 1.2. When you put the wrong frequency in for this bridge, if the wind was pushing at the natural frequency, that means that every time the wind blows, it adds more energy to the system every second. Then the oscillations get really big until they're uncontrolled. In the Tacoma Narrows Bridge incident, the wind was oscillating the bridge at exactly the natural frequency. The wind applied a force every few seconds. That every few seconds natural frequency of the bridge caused an increase in amplitude of the system. The bridge was oscillating with a higher and higher amplitude until ultimately it ended up falling apart. A wine glass does the same thing when you scream at the correct frequency. When you scream at the correct frequency, it vibrates the glass, and the glass vibrates at its own natural frequency, causing an increase in the amplitude of the vibration. That increase in amplitude will increase until the glass can no longer continue. The tension failed in the glass. It stopped being able to hold itself together because the forces were just too great, and it broke. So with this one I have a system with a magnet, spring, big solenoid. My solenoid is attached to a function generator that's going to provide some voltage here. All right, so what I want to do is put in voltage at exactly this frequency. If I can put it in at exactly this frequency, I can get resonance. I can push and pull on the magnet and make its vibration larger and larger, like this. So right now, let's not overcurrent it. I'm actually short circuiting the thing, which is why it's giving me a warning. So right now, what's going on is it's providing a periodic force at the frequency this thing wants to vibrate at. That puts more and more energy to the system every second. So it oscillates more and more and more. So one of the problems with resonance is sometimes you want it. When you want to make sound, like a note, if you want to make a resonance like a note for an instrument, you want resonance because then it means you have a nice, loud, clear sound. When you have something like a bridge, you probably don't want it to be gaining more and more energy every second. Mine keeps losing energy because the duct tape is hitting the edges around here. We'll be fine. This is an example of resonance because it's got this periodic force at the correct frequency for the system. So this system is 1.6 hertz. Every second, it pulls 1.6 times, 1.6 complete cycles per second. Okay. So if we have resonance, that's applying a periodic force at the natural frequency of the system. And this system is one-dimensional, it forms a circle, and it can definitely vibrate. So this is the natural frequency of the system, is that. Okay? So let's get the frequency down to what I want. That looks like something like 2 or 3 hertz. It's certainly not the 1,000 hertz it's normally set on. All right, and let's see if we can find where resonance is. So this is 1 hertz. It's vibrating up and down 1 time per second. 2 times per second. And if I find the right frequency, sometimes you can even see it. So let's see if you can see this. The other system is like still going in the background. Oh, it's almost there. You see this? Actually, I don't know if I need to put this on like a, let's make that lower voltage so it doesn't break my object. All right, I think we need a different background so they can see it more clearly. How about this? Can you see the shape it's making? At the resonance frequency of the system, it has some places where it moves quite a bit. Those are going to end up being called the antinodes later. See where it's moving like a whole bunch? Mm-hmm. And some places where it's not moving at all. These are going to be called the nodes later, the places where it's no motion. At the resonance frequencies, at the natural frequencies that it wants to vibrate at, sometimes you get really weird phenomenon. Right? So one of those you might have heard of before is the Chladni plates. And I might have to do some clever things with this one. The Chladni plates are going to be tricky just because I don't have my flexible camera here. All right. So same thing as before, right? We've got this system. Here, I'll pick it up. Right. It's basically a fancy speaker. It's putting a periodic force at whatever frequency I tell it to. And it's shaking a big plate that looks like a violin. We're going to turn that voltage down so it's not being so noisy. And we're going to turn the frequency up. Let's play around with that a little bit. All right. I've got this done. Let's see if we can find some patterns. So notice how on this frequency, do you guys see the lines that are forming on here? All right. So it's starting to form lines. I know this is a resonance frequency because where the antinodes are, it's vibrating a lot right here. And it's pushing all the sand to the places that aren't moving at all. If I keep upping this frequency, let's go up to something like uncomfortably high. All right, let's see if we get more patterns. Gotta find the new one. Ah, it's not coming up. Go, 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 go. There we go. Which is neat because if you're here, you can actually watch the sand like flowing to the spot where it wants to be. How about we lower that? Find the next one down from here. There it is.
Such a great noise. Sorry. All right, we'll turn off the loud noise. So these are all different natural frequencies for the same object. This one has a bunch of them, and the lab you're going to work on has a bunch of them as well. Your lab will make less annoying noises than this one. But you can tell the natural frequency because resonance will occur. And sometimes that makes really neat patterns. In this case, it makes patterns where the antinodes, where the places where it oscillates a lot, push all the sand away. Then there's whole stripes of places that don't move, making nodes where the sand will tend to accumulate because the net force there is zero.
So before I go watch this video, what I want you to do is I want you to pay attention to how the resonance frequency, the natural frequency as it's sometimes called, pay attention to how the natural frequency that you hear when they play the instrument depends on the size of the instrument. Check this out. How does the frequency depend on the length? Go watch this video in its entirety at some point, but I want to point out that if you increase the length, you hear lower frequencies. Larger objects have lower natural frequencies. Some common examples of this. This explains why men have lower voices than women. This is because men have Adam's apples. That larger chamber for resonance in your throat means that you have a lower frequency if you're a male speaker than a female speaker. Think about it in terms of instruments you know. A cello is a lot lower than a violin because it's larger. A cello is larger, and so it has lower frequencies. A ukulele is smaller, and it has higher frequencies. So with all the information in class today, you should be able to do homework 9.1, problems 1 through 5. Best of luck!